Have you ever tasted a lemon and felt your face scrunch up from the sourness? Or noticed how slippery and bitter soap feels in your hand? What you just experienced are two everyday examples of acids and bases. Acids: sharp, tangy, sour. Bases: slippery, bitter, soapy. Now imagine this. Someone in your family complains of acidity. What's your go-to remedy? A spoonful of baking soda, right? That's because baking soda is a base, and it helps neutralize the excess acid in the stomach. This is chemistry in action, and it happens all around us, even inside us. In this video, let's uncover how acids and bases behave, not just in textbooks, but in real life. You're about to see that the chemistry of sour and bitter is anything but boring. To understand acids and bases in the lab, we rely on something clever: indicators. Indicators are special substances that change color depending on whether they're in contact with an acid or a base. Here's how they work. Blue litmus turns red in an acid. Red litmus turns blue in a base. Phenolphthalein stays colorless in an acid but turns a bright pink in a base. Methyl orange: it turns red in acid and yellow in base. Now let's test your thinking. Imagine you're handed 3 test tubes. One contains distilled water, another an acid, and the third a base. You only have red litmus paper. How do you figure out which is which? Step 1. Dip red litmus into all 3. If it turns blue, that's your base. If it stays red, you've either got acid or water. Step 2. Now use blue litmus on the remaining 2. If it turns red, it's the acid. If there's no color change, that's your neutral water. Pretty neat, right? And indicators aren't just in labs, they're in your kitchen too. Ever noticed curry stains turning reddish brown when scrubbed with soap? That's turmeric, a natural indicator, reacting with the base in the soap. Now, let's dive into one of the most exciting reactions in chemistry: acids reacting with metals. Picture this: you drop a few pieces of zinc granules into a test tube of dilute sulfuric acid. Within seconds, bubbles begin to rise. What's happening? Those bubbles are hydrogen gas escaping. The reaction follows a simple pattern. Acid plus metal gives salt and hydrogen gas. For example, HO plus ZnZnSO plus H. Spelled H2SO4 plus Zn gives ZnSO4 plus H2 gas. And here's a fun way to test for hydrogen. Bring a burning candle close to the mouth of the test tube. Pop. That sound confirms hydrogen is present. This isn't just a textbook reaction. In laboratories, this is how hydrogen gas is often collected, even used to fill balloons. So the next time you hear a pop in the lab, it's not just sound, it's science speaking. We often talk about acids reacting with metals. But what about bases? Let's explore a lesser-known but fascinating reaction. Take a strong base like sodium hydroxide. Now add some zinc metal to it and gently heat the mixture. Guess what? You'll see bubbles again. Yes, hydrogen gas is being released. But here's what's different. The salt formed this time is called sodium zincate. The chemical equation looks like this: 2NaOH plus Zn Na2ZNO2 plus H2S. Spelled out, 2 molecules of sodium hydroxide plus zinc give sodium zincate and hydrogen gas. So what does this tell us? Bases, though usually gentle, can react with certain metals just like acids do. And yes, hydrogen gas is still produced in the process. Not all metals show this behavior, but those that do remind us. Bases can pack a punch too. Let's look at another important chemical reaction: when acids meet carbonates. Take a spoonful of sodium carbonate and add a few drops of hydrochloric acid. Instantly, you'll see fizzing bubbles rise. That's carbon dioxide gas being released. Here's the reaction: Na2CO3 plus 2HCl 2NaCl plus H2O plus CO2, spelled out, sodium carbonate plus hydrochloric acid produces sodium chloride, water, and carbon dioxide gas. Want to test for carbon dioxide? Just pass the gas through lime water. It turns milky white, confirming its presence. But this isn't just a lab trick. This very reaction is used in soda acid fire extinguishers. The carbon dioxide gas released smothers the flame by cutting off its oxygen supply. From classroom beakers to real-world safety, chemistry makes it all possible. So what happens when an acid meets a base? They don't clash. They neutralize each other. The result? A harmless combination of salt and water. This process is called a neutralization reaction. Let's take a classic example. NaOH plus HCl, NaCl plus H2O. Spelled out, sodium hydroxide plus hydrochloric acid produce sodium chloride, common table salt, and water. Simple but powerful. This reaction is the science behind antacids like milk of magnesia. When your stomach produces too much acid, the base in the antacid neutralizes it, bringing instant relief. So next time you reach for an antacid, remember, it's neutralization in action. Now, let's dig a little deeper into the world of oxides. Start with metallic oxides, like copper oxide, a black powder. When you add hydrochloric acid, a reaction takes place, forming salt and water. The equation? QO plus 2HCl. QCl2 plus H2O spelled out, copper oxide plus hydrochloric acid produces copper chloride and water. This behavior tells us something important. Metallic oxides are basic in nature. Now flip the situation, take carbon dioxide, a non-metallic oxide, and react it with a base like calcium hydroxide or lime water. What happens? CO2 plus CaOH2, KCO3 plus H2O. That is, carbon dioxide plus calcium hydroxide gives calcium carbonate and water. This reaction shows that non-metallic oxides are acidic. They react with bases just like acids do. So here's the takeaway. The type of oxide, metallic or non-metallic, gives us a strong clue about whether the element is basic or acidic in nature. Let's take a quick recap of what we've explored. Acids react with metals to release hydrogen gas and form salt. Bases, though less commonly, do the same with some metals. Acids plus metal carbonates produce salt, water, and carbon dioxide. Acids plus bases, they neutralize each other to form salt and water. Metallic oxides behave like bases. Non-metallic oxides behave like acids. But here's the real magic. This chemistry isn't just confined to labs. It's happening all around you. Got acidity? Antacids like milk of magnesia use bases to neutralize stomach acid. Fire emergency? Soda acid fire extinguishers release carbon dioxide to put out flames. Curious at home? Turmeric and red cabbage make excellent natural indicators. Tooth care? Toothpaste helps fight acid in your mouth. A perfect example of neutralization. So next time you clean with soap, taste a lemon, or feel that bee sting, remember, acid-base chemistry is quietly at work. In the next video, we'll dive deeper into the secret behind all acids and bases, what they truly have in common, and why water holds the key to unlocking their behavior.